So moving on to lesson 4, we're talking about more optimization questions. There are two of them. One of them, and these are both involving cost, so we're talking about the dollar value of a quantity, not just the volume or surface area, but the specific cost of constructing an object. So there's one here about a rectangular field that has to have a certain area, and one type of fence costs this much, the other type of fence costs that much. So how do we minimize the fence or the cost? There's this other one here about the rectangular box where again you get sort of the same concept. So again, when you're optimizing, it's always this 6-step procedure where you are, what is it, the quantity you're trying to optimize? In this case, we're trying to optimize the cost. The constraint here is the area. We know that it has to have an area of 100. So in this case, we can construct an equation: area equals length width, and this means that length width equals 100 in the case of this particular question, right? Because it has to have an area of 100 meters squared. That is the constraint that's holding us back. We need to use the constraint to isolate a variable, create a function that only uses one variable, right? That we can then use our calculus techniques to optimize, find its domain, and then we can check all the extreme values and get our answer. So let's just think here, we're trying to optimize the cost, and we know that the cost is related to the perimeter of the fence. So let's start with what we do know. The perimeter of the fence is 2L plus 2W, right? To make a rectangular field, to fence in a rectangular field, you're going to need 2 lengths and 2 widths. Of course, we're not actually trying to minimize the perimeter. We're trying to minimize the cost. And the cost, we take our 2L plus 2W, and we now go back into the question and read about how different things cost different amounts. So for example, our north-south sides each cost $20 per meter. So let's say W will represent our north-south sides. We're going to have to multiply each of those by 20, right? Because if we have 1 meter of fence going that way, it's going to cost us $20 for that meter. So we multiply that by 20. Again, we're going to multiply this by 5 to show the same reason. And so what we're saying here is that L is equal to the east-west fence, and W is equal to the north-south fence. So this is why it is, multiplied by 20, and this one is multiplied by 5, right? You want to think about why I'm doing this, right, in terms of creating an equation that models the cost. So we've created a cost equation that is 10L plus 40W, and that is the equation that we are trying to minimize. Okay, of course, this has two variables right now, an L and a W. So if I was going to try to differentiate it, would I differentiate it with L or with W? And regardless of which one I picked, one of them would have to be implicit because it's a different variable. So I don't want to work with two variables. I want to use my constraint, okay, to isolate a variable. So I know from my constraint equation above that LW equals 100, and therefore 100 over L is equal to W, right? I can isolate W according to that equation. And I can now rewrite anywhere I see W in my original cost equation, I can now change it with 100 over L. So let's do that. I can now create a cost function, okay, where I can do cost in terms of L would be equal to 10L plus 40, 100 over L. Okay, and what's going on there is, again, I'm looking at my cost equation from above, and I'm just swapping W with what I know W to be equal to. If you like, we can just quickly give that a different color to sort of show that we're, what we're doing the substitution for here. We're changing out W with what we know W to be equal to. The reason that we do this is so that we can create a function. The function only works, in terms of one variable, and we get 10L plus 4,000 over L. And this is an equation that, we can definitely, minimize the cost of. So state the domain of the function. It stands to reason that 0 is the lowest value for L that would realistically make sense. The highest value for L, we can't really actually say, because you could imagine a length of, 100,000 with a width of, a few millimeters, and it would have the right area. So again, this is an unbounded question. I don't really have an upper bound here, so I'm going to write under this. I'm just going to write, that there is no upper bound since there is no limit to how long the field could be. Of course, we know that a very long field is a very inefficient field and not going to be our answer, so this probably gives us reasons to think whatever we get for a critical point is likely to be our answer. So the extreme values, the candidates are as follows. It could be the cost of so one candidate is C of 0. Could be one of the costs. Of course, if we try C of 0, we get 10L over 4,000 over 0. So I'm doing here, which of course is undefined. So like in the previous question, we know that this really is not going to be our answer. C of 0 is not going to be an answer. So, C of 0 is out. C of a very, very large number is out. So, what we're left with is C of whatever the critical point is. So that's why we're going to find it. So let's take our equation, which is up here. And we'll just get to a new page here and start taking the derivative. So again, it might make sense to just rewrite this as 4,000 L to the power of negative 1 so that we can sort of easily use a power rule. C prime of L is then equal to 10 minus 4,000 times L to the negative 2. And an easy way of writing that is C prime L equals 10 minus 4,000 over L squared. Okay, and we get that. This we're going to set equal to 0, 10 minus 4,000 over L squared. And, as usual, we want to get rid of that denominator, so we're going to multiply each term by L squared. And what that does, of course, 0 times L squared is still 0. We get 10L squared, and then we get minus 4,000. That denominator has canceled out. To solve the problem, we end up with 4,000 equals 10L squared, which means 400 equals L squared, which means plus or minus 20 equals L. Now, minus 20, I'm going to reject because it's outside the domain. Please make sure you write this. It might seem inane, but part of what I'm checking to see that you understand is that the values you consider are only the values that exist inside the function's domain. If you don't tell me that you're doing that, I cannot read your mind that you're doing that. So 20 equals L is when, so let's put it another way, C prime of 20 is equal to 0. And this means that 20 is a critical point. So if we look, we can go C of 20 is equal to 10 times 20 plus 4,000 over 20. Right, so I believe what our equation was back up here, our cost equation is 10L plus 4,000 over L. So get this, and we get that the cost of this, the ideal field here, has a cost of 200 plus another 200, which is 400. Quickly, just to show how we could design this in GeoGebra, we could quickly make our equation as follows. We know that the width function is equal to 100 divided by L. I'm going to have to use X in GeoGebra. Actually, I can quickly use Lx equals X. I can do this over L. Okay, so we get, this is our width and length function. We then know that the cost of it was 2 width, so the area, it's 2 width times 20 plus 2 length times 5. That was our cost function from before. I'm just going to rename it to C. Okay, so the cost of building this thing, you can see, looks like this. Now, of course, we're really only interested in this function from 0 onwards, so let's draw it from 0 to 4,000, for example, and we can just kind of drop the left side. We're not that interested in the left. You can kind of see how this function behaves here, right? It has an infinite discontinuity at 0 because, of course, trying to build a fence with a 0 length is going to take an infinite width to get the area, right? So we rejected that. We knew that a very, very large field in terms of one dimension would mean the other dimension is very small, which would be a waste of, would be very inefficient. So we only found the one critical point, and the critical point we found was 20 and 400, right, which you can see right there on the graph. And again, if we draw a tangent AF, we get a flat tangent that shows us that we should be quite confident that this is the minimum. The other thing you can do, you can check the second derivative, or you can make a quick interval table and show that this must be a minimum. Now, we've already checked all the we know that the minimum here has to be either C of 0 or C of 20. Since C of 20 is lower than C of 0, we can conclude that it has to be the extreme value. If you weren't confident of that, then what you do is you take the derivative of cost, which we already have. There's C prime from before. And you just analyze this around the number 20. At 20, it's 0. Before 20, it's negative. So if you want to imagine, here, let's draw a little interval here at x equals 20. Over here, left of it, right, we have c prime of x is less than 0, which means that the cost is decreasing. So the bigger we make our function, the cost is decreasing. Now, on the other side, you can see that c prime is positive. Over here, sorry, just fix this up so it says the right thing. And therefore, the cost is increasing. Well, if the cost goes from it decreasing to increasing, then we've just proven that a local min has to have occurred, right? Because your slope is going down, and then it's flat, and then it's going up. So you've proven to me that it's a minimum. You've checked the point. You've shown that it has a lower value than any other candidate. The only other candidate was 0, which is kind of a nonsense point in this example. And that therefore this is a minimum, and it is the lowest point that could be created. And that's why when we look at our function, this is the point where the cost stops dropping and then starts to rise. So this is the ideal fence that we can construct. Now, as a final step to these questions, I want you to go back and read what it actually says. It says, what are the dimensions so the cost is a minimum? This means we go back and we say the dimensions that produce a minimum cost are when the length is equal to 20, which means the width has to be equal to 5. Equal to 5 meters. Recall that the total area has to be 100, right? 100 equals total area, or another way of saying this is width equals 100 over length. So that's how I'm getting, the 5 there. I'm just doing 100 divided by 20. So this tells you the dimensions, and that's what you were actually asked for. So we found a minimum. We're confident it's a minimum. It's the lowest possible fence you could make, right? It's the best possible scenario. And I've answered the question in terms of giving them the dimensions that they asked for. The length is 20, the width is 5. Okay, so that takes care of this question. If you just want to click on to the next video, we'll cover this last one about the open top box.